Every edge AI deployment faces the same immovable constraint: the power envelope is fixed before the first line of code runs. The architecture that emerges is not arbitrary. It is a direct consequence of thermal physics, battery chemistry, and enclosure geometry. This teardown examines what a class of embedded AI Accelerator SoCs reveals about how that constraint propagates through every design layer. The system is a heterogeneous SoC built for real-time AI inference outside the data center. 4 functional domains: an ARM CPU cluster for scheduling and control plane logic, a shader-based GPU for parallelizable tensor operations, a purpose-built deep learning accelerator, the DLA for fixed topology inference graphs, and a shared LPDDR memory pool accessed by all 3 domains through one unified memory controller. No discrete VRAM. No PCIe interconnect. 1 die, 1 memory bus. Total thermal design power spans roughly 5 watts at the floor to 60 watts at the performance ceiling. That range is not a product feature. It is a design constraint. Every architectural decision in this system is a response to the same question. How do you fit data center class AI inference into a power budget measured in watts, not kilowatts? First choice: unified memory architecture. Discrete GPU systems run 2 independent memory domains, GDDR6 on the GPU, DDR on the CPU, connected by PCIe. That configuration maximizes per domain bandwidth. GDDR6 delivers over 900 GbS to the GPU. The problem is power. A PCIe X16 link at high utilization consumes 8 to 10 watts. On a 15-watt total platform budget, that is an unacceptable tax before a single inference operation runs. The rejected alternative is exactly the discrete configuration that dominates data center hardware. The accepted trade-off is a single shared LPDDR pool, 136 GbS on current implementations, split dynamically between CPU and GPU workloads. Peak GPU bandwidth is roughly 1/6 of a discrete card. What you recover is zero-copy tensor sharing between the CPU preprocessing stage and the GPU inference stage. Removing that DMA transfer cuts pipeline latency 15 to 40 milliseconds per frame on compressed sensor inputs, depending on frame size. The bandwidth loss is real. The latency recovery is also real. Which matters more depends entirely on your pipeline topology. Second choice: integrating a fixed-function deep learning accelerator alongside general-purpose GPU cores. The constraint is inference throughput per watt on stable, known network topologies. A GPU is programmable. That programmability has a power cost, control logic, register file, instruction dispatch hardware, none of which contributes useful work when executing a fixed convolution graph. A DLA is a hardwired data flow engine. Matrix multiply, convolution, and activation operations are committed to silicon with no instruction fetch overhead. At INT8 precision on a RAISE-net 50 class network, the DLA delivers roughly 4 times the useful operations per joule compared to the GPU on the same SoC. The rejected alternative is GPU-only inference, a simpler software stack, and full compatibility with any model operator. The accepted trade-off is a 2-tier execution model. Validated, compiled graphs run on the DLA. Models with dynamic shapes, custom operators, or unsupported activations fall back to the GPU. The operational implication is non-trivial. Any model update that introduces an unsupported operator drops the entire inference task off the DLA and back onto the GPU power budget. That creates a hard integration gate. Every model revision requires DLA compatibility verification before deployment in a power-constrained system. Third choice: configurable TDP with discrete software-managed power modes. Embedded deployments do not have a fixed thermal environment. A payload integrated into a ground vehicle on a hot day operates under a different thermal ceiling than the same payload on a high-altitude platform in cold air. A fixed TDP processor forces the cooling system to size for the worst case, which consumes enclosure volume and mass in every other operating condition. The rejected alternative is fixed TDP, simpler power delivery circuitry, predictable performance, no software complexity. The accepted trade-off is a power mode abstraction that simultaneously caps CPU frequency, GPU clock, and memory bandwidth. The cost is performance non-determinism. A platform that transitions power modes under thermal load produces throughput variance that propagates directly into sensor fusion pipeline timing. Managing that variance requires explicit power mode contracts between the application layer and the hardware configuration layer. In a defense integration program, those contracts belong in the interface control document and must be verified at subsystem integration test, not discovered during operational evaluation under thermal stress. Read the three choices together. Unified memory is a power decision, not a preference for architectural elegance. The DLA exists because the GPU draws too many watts executing fixed-function workloads. Configurable TDP exists because the thermal environment varies with the mission. Every decision traces back to the same root, a fixed power envelope. The practical implication for a program office is this: the most useful specification for any edge AI platform is not peak tops. It is power-normalized throughput at your operational TDP ceiling. A platform advertising 275 tops at 60W is a categorically different system from one delivering 40 tops at 10W if your enclosure thermal budget is 10W. The first number is irrelevant. The SWaP-C constraint does not relax because the mission requires more compute. It forces the architecture to trade flexibility for efficiency, and that trade surfaces at every layer. The right question for any edge AI platform evaluation is not how fast it runs. It is, what is the power normalized throughput at my operational thermal ceiling, and what model classes execute reliably within it? The architecture answers that question in silicon. Your job is to read the answer before you commit the integration budget.